Welcome to our project. Today we'll be showing you our development of a COANDA-directed compressor cavity injection design for Honeywell Aerospace. We'll walk you through the design process from start to finish, all while giving you a closer look into a typical test day here with Team 26032. Come on!
Typical turbofan compressors are not perfectly efficient. Pressurizing the high-speed flow often results in air that leaks in different parts of the compressor. For a Honeywell Aerospace turbofan engine, the leakage flow is redirected into a hub cavity between two stator blade arrays. The current design injects air normal to the main flow path, causing irregular pressure gradients downstream, reducing stall margin and increasing fuel burn.
The goal of this project is to investigate alternative injection methods that employ the COANDA effect to analyze their impact on the downstream pressure gradient.
Put simply, the COANDA effect is a natural tendency for a jet stream to attach to a nearby curved surface. Surrounding air gets pulled along by the jet's curved path, also known as fluid entrainment. The ability for the fluid to stay attached to the surface is all dependent on the radius of the curve, the slot width that the jet exits from, and the momentum of the jet stream. We developed our COANDA injectors to test variations of these parameters.
Our design is a wind tunnel experiment that features a secondary flow stream injected into the test section with a single vertical airfoil representing a stator vane. The geometry of the injection varies with a modular component that can be swapped out between different test configurations. We use computational fluid dynamics to inform the design of the injector and provide a flow model for the entire test section that we could compare to our measured results.
Good. There were several major system requirements that drove this project's design. Edward, hit it! We were required to recreate the Honeywell injection problem. For our injector design, the mass flow rate of the SFS was required to never exceed 2 to 3% the flow rate of the wind tunnel itself to more accurately simulate the conditions in the compressor. We were also required to reduce the adverse pressure gradient caused by radial injection by at least 40%.
The modular injector and the COANDA-directed geometries were developed in tandem with the secondary flow system.
The SFS draws air from the AME lab supply and delivers it to a PVC T-bar. The T-bar has a series of 12 outlet holes to dump pressurized air into the injector plenum and transition it into a free-stream jet sheet. Compressible flow analysis were conducted to ensure the holes would choke the flow, aiding in uniformity.
We calculated mass flow rates by measuring the hole exit temperature during preliminary secondary flow system tests, later buying a flow meter to measure this directly. The final system features the flow meter, T-bar, and a pressure regulator between the two. We verified this system through multiple full pressure tests and leak analysis by applying soap to joints and monitoring pressure drops downstream.
Within the test section, the airfoil is subjected to a regular loading by the injector and the free stream.
Doing FEA allows us to learn about how much stress the airfoil is under as well as how much it deforms because of the lift and drag forces acting on it in the wind tunnel. We learned that fixing the airfoil at both ends and running a metal rod through it makes it deform less but also increases the stress in certain areas. Just fixing the airfoil at one end and not having a metal rod run through it allows it to bend slightly, reducing stress.
The airfoil and connecting plate were manufactured at the Engineering Design Center with 3D printing. The AME machine shop was used to cut our 3 custom acrylic panels by utilizing a mini CNC router and by hand tapping the threads, as well as the shop being used to create our metal pitot rake adapters, where all the creation of this hardware came to be with the help of the GOAT, Joe Hartley.
To configure the wind tunnel, we designed custom acrylic panels for the walls and top ceiling of the test section. These panels had cutouts for all the necessary subcomponents: the modular injector, pitot rake, pitot-static probe, and the airfoil stator vane. The data we collected was the downstream total pressure near the ceiling using a wake rake and the static pressure using a pitot-static probe. This was all processed through LabVIEW software and verified to be running correctly using an ambient calibration pressure test without any slot injection.
Using the ANSYS Fluent software, we successfully modeled the CFD simulation of our wind tunnel and SFS injection. The results showed the COANDA injection geometry, creating high-pressure flow regimes at the ceiling. We also saw low-pressure dips around this region at the trailing edge of the airfoil, which would later match what we saw in testing. But compared to a radial injector case, a large low-pressure region was formed around the center of the test section with turbulent flow around the stator. Simulations suggested that the COANDA pressure drops were roughly 0.2 psi, with uniform flow everywhere except the injector wake. Compared to the baseline, which saw drops between 0.3 and 0.5, this was a significant improvement.
Our experimental test results validated that the COANDA-driven geometries successfully controlled the flow of the leakage injection air. Throughout each test, the mass flow rate of the secondary flow system maintained the requirement of 2 to 3% of the free stream mass flow rate. As part of our requirements, we implemented flow viz techniques to understand how the leakage air was interacting with the main flow along the stator and injection surfaces. Our first technique, known as surface tufting, can be seen here. The baseline injector case shows chaotic and turbulent behavior as the leakage air impinges the main flow. COANDA Surface 3 causes the flow to remain straight and attached around the stator, which is a product of fluid entrainment. The following total pressure data was taken at the same operating conditions. The no injection case shows a pressure deficit of a very small magnitude compared to the baseline injection case, where a wider spread and larger pressure drop can be noticed. This behavior represents the problem statement provided to us, where a radial injection causes an unpredictable pressure drop. On adding our COANDA-directed flow, we've noticed a positive jet contribution behind the airfoil, with COANDA Injector 1 bringing the pressure closest to the ideal no-injection case with a small overshoot compared to the other COANDA cases. Therefore, we've successfully met the requirement of improving the adverse pressure gradient of the baseline injection case by at least 40%. However, we did overshoot this by adding an unwanted positive pressure profile. Exploring lowering the momentum of the injector may help us find a balance between creating a deficit versus a strong jet. We also found that using a finite rather than infinite slot introduced edge effects and enhanced boundary layer effects around the corners of the slot located at plus or minus 0.625 of the normalized rake position. We believe this complex behavior also impeded the accuracy of pedostatic measurements of the slot exit.
The primary challenge we faced was having unwanted leaks in the system. We were able to reduce them but were unable to make it completely leak-proof while maintaining the modular design. Improving the mating between the injector and SFS potentially by transitioning to a permanent fixture could eliminate leaks and maximize total pressure. We met our system requirements, but it might be of benefit to investigate if dropping the pressure of the secondary flow system while keeping the type of COANDA geometry used constant decreases the magnitude of the jet contribution and momentum in the future. Overall, this project gave us a strong foundation in subsonic, high-pressure wind tunnel experimentation and major insight into the COANDA effect and its use cases.